Okay, so this is 5.11 notes, solving optimization problems. In 5.10, we talked about the 5 strategies on how to solve these problems. In actuality, these first 3 are 5.10. That's what's us setting up the problem in 5.10. Now we're going to look at those same problems in 5.11, but now we're going to actually solve for the maximum and minimum values depending on whatever the problem is asking us. So before we start, I'm going to go to the margin. We're going to write a couple notes. Okay, recall that we can find absolute extrema values from critical points and what? So, not points of inflection. Endpoints. Okay, and that's of course if they give us an interval to test. Okay, recall that if we only have one critical point, that is also a relative max or min value, then that critical point must be a what? An absolute maximum or minimum. So if we only have one critical point, which means we take the derivative, we set it equal to 0, we only get one possible value for x, and that possible value for x is a possible relative maximum or relative minimum value, then it must be considered an absolute maximum or minimum. So again, in these problems, I'm going to be taking the equations that I found from 5.10 in order to continue solving. So it might be a little confusing if you haven't looked at 5.10 yet. So number 1 is going to be us continuing number 2 from 5.10. In that example, it was asking us what point on the graph y is equal to the square root of x is closest to 5, 0. So here's the point 5, 0. And it wants us to find an approximate value. And we determined that that approximate value is going to come from the distance formula here. When we plugged everything into the distance formula, we got d is equal to the square root of x minus 5 squared plus x. Okay, all under that square root. Again, in 5.10, I show you how to get to this point. Okay. We also determined that the point that we're trying to estimate is going to be x comma the square root of x. So in order to find the point closest to 5, 0, we're going to take the derivative and then set that derivative equal to 0. So we know that another way to rewrite this radical is to write it as an exponent. So this could be x minus 5 squared plus x to the 1/2 power, which makes it easier for us to take the derivative by using the power rule and then eventually the chain rule. So d prime, the derivative would be what? 1/2, everything inside there, yep, to the power of negative 1/2, and then using the chain rule, what's going to be next? Times, so we have x minus 5 squared, so we have to take the derivative of that, doing 2 times x minus 5. Okay, we technically take the derivative again inside of that parentheses, but what's the derivative of x minus 5? 1. So do we need to say times 1? No. But then we have to take the derivative of that plus x. So that's going to be plus 1. Okay, so this whole thing is the derivative. I'm going to rewrite this so we take the negative exponent and move it down to the denominator. So this is the derivative of d is equal to 2 times x minus 5 plus 1, so that all that second part that we have at the end, over 2 times the square root of x minus 5 squared plus x. Okay, so I just moved this entire part here to the denominator because of that negative exponent, and then everything that was left remained on the numerator. Okay. Now I need to set this derivative equal to 0, which means really, what am I setting equal to 0? The numerator. So I have 2 times x minus 5 plus 1 equals 0. What's my first step to solve? I could move the 1 first, or I could distribute the 2. So I have 2x minus 10 plus 1 equals 0. That way I can combine like terms. And so I have 2x minus 9 equals 0, which means x equals 4.5, or as a fraction, 9 over 2. Okay, so yes, we could write this as 9 over 2 or 4.5. However, is that the answer the problem was looking for? No, it was looking for the point. And we established in 5.10 that that point is x comma square root of x, which means our answer is 4.5 comma square root of 4.5. That is the point that is the closest on the graph y equals square root of x. And that point is about right here. So again, this was us continuing number 2 from 5.10. So in reality, if you are given a problem like this, it's not going to be broken apart. They're not going to say, okay, only draw the diagram and set up the equation, or only solve. It's going to be one entire problem that you would work through. Okay. The next one, number 2, is actually number 4 from 5.10. And when we were drawing this diagram for number 2, it looked like 2 right triangles facing each other. So it says 2 towers are 30 feet apart. One is 12 feet high and the other is 28 feet high. There is a stake in the ground between the towers. The top of each tower has a wire tied to it that connects to the stake on the ground. Where should the stake be placed to use the least amount of wire? So when we did this problem on 5.10, we found the following equation. And that was the equation for the length of the wire. So L is equal to the square root of 784 plus x squared plus the square root of 144 plus 30 minus x squared. So again, we found this equation in notes 10. We're going to do the same process we did above. We're going to find the derivative and set the derivative equal to 0 to figure out where this stake should be in the ground in order to use the least amount of wire. So taking this derivative, we have to remember that a radical, especially the square root, can be rewritten as an exponent to the 1/2 power. So knowing that, we have 1/2 784 plus x squared to the negative 1/2 power times what? So we have to use the chain rule here. Times 2x. Right? Because the derivative of 784 plus x squared is 2x. Then we do the same thing for the next radical. So this is going to be plus 1/2 times 144 plus 30 minus x squared to the negative 1/2. And then we have two chain rules inside of here. We have to deal with the exponent for the 30 minus x squared and then take the derivative of that inside function. So what am I going to be multiplying by?
2?
Not just 2.
Oh, it would be 60 minus 2x.
Okay, yes. I'm just going to write it out before you distribute it. So it's 2 times 30 minus x, right? So we bring the 2 down. And yes, if we were to distribute that 2, it would be 60 minus 2x. And then we have to take the derivative of 30 minus x, which is negative 1. Okay, so that entire thing is our derivative. So what I'm going to do now is I'm just going to rewrite this where all the negative exponents go down to the denominator. So this is L prime is equal to x over the square root of 784 plus x squared minus 30 minus x over the square root of 144 plus 30 minus x squared. And how I got that is I noticed that the 1/2 and the 2x here, the 1/2 and the 2 are going to cancel, and I'm just left with the x on top. On the next fraction, the 1/2, the 2, and the negative 1, the 1/2 and 2 cancel, and then I'm left with a negative instead of a positive here, so that's why I'm subtracting. And then whatever was left went on the top, and then the entire thing that had the negative exponent went on the bottom. So remember, our goal here is to set the derivative equal to 0 and solve. However, this is not going to be as easy as number 1. Because if we were to do this by hand, we would have to get a what? Not a GCF. We have two fractions here that are subtracting. So we'd have to get a common denominator, and I don't know about you guys, I don't want to do that. That's a little crazy with those radicals in the denominator. So that's why we have Desmos. So if you don't have Desmos open, go ahead and open that up. And on Desmos, what we're going to use is the InSolve feature. And you recall that we change all the x values to x sub 1. And we change the equal to that tilde, the squiggle. Okay, so I'm going to open up Desmos as well. Desmos not on here. I didn't mean to do that. Let's try that again. There we go. Get rid of the stats. Okay. So what we're going to do on Desmos is we are going to type in the entire derivative, exactly how we see it, and we're going to set it equal to 0. So this is going to be x sub 1, so you just put a 1 next to it and it does it for you, divided by the square root of 784 plus x squared, or sorry, x1 squared. We have to always forget, we always have to remember to put the 1 next to it. Okay, or it won't work. Okay, minus, and then we have 30 minus x sub 1 divided by the square root of 144 plus 30 minus x squared. Okay, so x sub 1 and then squared. Okay, so that's my derivative. I just switched out all the x's for x sub 1, and I'm going to set this equal to 0 by using the tilde and then 0 and Did I type it in wrong? Oh, I forgot. Yes. This part, thanks. That's still not correct, though.
The square is still on the inside.
Oh, yeah, okay. Okay, there we go, 21. That's what we should get, 21. Thank you. It's a lot harder to do on the iPad than on the keyboard. Okay, so x is equal to 21. So that is what we were trying to find. But remember that x is representing where we're putting the stake. So what is going to be the units attached to 21? Feet. So we have x is equal to 21 feet. That's our answer. Okay. Okay, number 3. So number 3 is, we don't need to rely on any information from 5.10. So this is like a brand new problem. It says a particle is traveling along the x-axis and its position from the origin can be modeled by x of t is equal to such, where x is centimeters and t is seconds. So it says on the interval where t is between 3 and 9, find when the particle is furthest to the right. So this right here tells us that we're looking for the largest value. Okay. So in order to decide this, we have to find those critical points. In order to find the critical points, we have to take the derivative. And when we take the derivative of the position function, what are we really finding? Velocity. Okay, so we're going to say v of t is equal to the first derivative of the position function, and that gives us 3t squared minus 30t plus 72, and then we set that equal to 0 to find potential critical points. Before I factor this, I can take out a GCF of 3, and I'm left with t squared minus 10t plus 24 equals 0. And what would be the factors for this? 6 and 4, both positive, both negative, one of each. One of each? No. Both negative. So we have t minus 6 times t minus 4 equals 0, because negative 6 and negative 4 give us positive 24, and negative 6 and negative 4, when you add them, gives us negative 10. So that means we have the critical points t is equal 6 and t is equal to 4. So before we plug these in, we have to remember that we also need to include what? The endpoints. So not only are we going to be plugging in 6 and 4, we're also plugging in 3 and 9. And we're going to plug that back into the position function. So this is x of 3, x of 4, x of 6, and x of 9. And since we have Desmos here, I think the easiest way to do this is to type in your position function into Desmos, and then on the next line, plug in that value. And in order to do that, you're going to need to use f instead of x. So it needs to be f of t, or it won't work. Okay? So let's pull that up here.
You could just replace t with x.
Or you could replace t with x, but then it would be x of x. Yeah, so either way, you're going to have to replace something. So I'm just going to do f of t. So I have f of t is equal to t cubed. You know what? I am just going to do f of x and replace it with all x. I don't want to keep going back and forth. Equals x cubed minus 15x squared plus 72x minus 9. Okay, so that's my function. I just replaced t with x. Now on the next line, I'm going to use these values, 3, 4, 6, and 9. So I'm going to do f of 3, and I get what?
99.
99, so this is 99. And then I'm going to do 4, and I get 103. Then 6, I get 99 again. And then 9, 153. And remember, I said the furthest to the right means the largest value. So which t value gave us the largest value?
9.
T equals 9. So this is when t is equal to 9. So this is our answer right here. X of 9 equals 153, and that is when t is equal to 9. Okay. And then the next part here says on the same interval, so we're still using t between 3 and 9, what is the particle's maximum speed? Okay, so before we can establish this, we need to find acceleration. Okay, because acceleration is going to give us our inflection point to check. We will check our inflection point and we will check our two endpoints. So we know that acceleration is equal to the derivative of velocity, which is the second derivative of the position function. So taking that derivative, we get what?
16 minus 30.
6t minus 30, set that equal to 0, and that means t is equal
5.
to 5. Right? We add 30 to the other side. 30 divided by 6 is 5. Okay, we're then going to take that value with the endpoints and we're going to plug it into velocity. So we're going to find v of 3, v of 5, and v of 9. Okay. So we're going to do the same thing and we're going to this time write the equation for velocity, which was 3t squared minus 30t plus 72, and plug in 3, 5, and 9. So what you should get for v of 3 is 9. For v of 5, negative 3. And for v of 9, 45. But since we're talking about speed, we know speed is what? Absolute value of velocity. So really, we're taking the absolute value of each of these, which is going to turn them all positive if they're not already positive. And since we want the maximum speed, we're going to look for the largest number, and that's going to be what? 45. So our maximum speed is 45, what? What's the units?
Centimeters per second.
Centimeters per second. That's our answer.